Hey everyone, in this video we're going to tackle hypothesis testing. So we're going to go over the basics of hypothesis testing and then we're going to do an example with testing for a proportion. So we're kind of going to do it all together. So the background here for this example is there's a legendary story on college campuses concerns two students who miss a chemistry exam because of excessive partying, but blame their absence on a flat tire. The professor allowed them to take a makeup exam and he sent them to separate rooms to take it. The first question, worth 5 points, was quite easy. The second question, worth 95 points, asked which tire was it. So, which is pretty clever, right? I asked you to complete the tire survey, so hopefully you have already done that before continuing to this notes. And so I can collect the data. So later on, I'll show you what the data, and I did combine it with my other stat classes so that we have a larger sample. So the question that I asked you is which tire will you pick if you were caught in that situation? And so for some reason, I conjecture that college students appear to have a tendency to pick the left front tire. I don't know if maybe because that's the driver's side, I just kind of envision that people will pick that tire most often. So you will use this data to conduct a test of whether the sample data provide convincing evidence that the left front tire is picked more often. So here, this is when you're reading a study, the wording is important. So here, we want to see if the data provide convincing evidence that the left front tire is picked more often than we would expect if the four tires were picked equally often. So here, I'm going to highlight that because this is going to help us set up our hypotheses. So first, let's ask the research question. Is the left front tire chosen more often than the others? Than if they were chosen equally, right? So then what are the observational units? Well, I'm thinking college students, so ARC students is what I'm looking at as the observational units. That's where I'm taking my survey from. What is the variable that is measured on each observational unit? The tire chosen. And here I wanted to make it a binary variable. So even though the variable itself is not binary, right, because there are 4 tires, the left front tire is just 1 out of the 4. So it's not really binary, but I want to make it binary. So what I do is we say we're going to keep track of left front tire or not. So the variable then is, was the left front tire chosen? And then the answer will be yes or no. And so now it's a binary variable, 2 categories. Give some information about the sample of individuals that participate in our study. This is a convenience sampling of STAT 300 students in my classes. So it's not a simple random sample. Ideally, you want to make sure that you have a simple random sample. This is a convenience sampling, but we'll go ahead and still use the test of significance to see about the claim. The claim is that I think the left front tire is picked more often than expected by random chance. So here's the data from the survey of the people who took the survey from all my STAT 300 classes, so 37 in total, so a little less than before. So let's calculate the observed statistic. So what proportion of students selected the left front tire? So again, notice the wording, what proportion selected the left front tire. So this helps us identify what variable we want. So which one represents proportion? P hat and pi. So let me call that actually P. Our book uses P most often. So we can say it's either going to be P hat or P. So the question is then the observed statistic. So which one represents the statistic versus a parameter? And P hat is the statistic, right? So then we're going to say here that P hat is equal to what? I'm going to insert an equation. Oh, wait, I can't do that. Oh, I already had the menu there, that's why. So we're going to choose the one with the hat. So P hat is equal to, and we're keeping track of the left front tire. So it's going to be 11 out of 37. So I guess I can, since I already have that menu there, probably use the fraction. So 11 out of 37. And we can put that on our calculator and get a decimal. So when you do 11 divided by 37, we get 0.297. So let's round to 0.30. So then this becomes our sample statistic. So the 0.30, we don't know the population parameter. So in the previous sections, we were using confidence intervals to try to estimate the population parameters. Here, we're just trying to see a test of significance and saying, okay, do people choose the left front tire more often? So now notice that our sample is 0.30. What if we were just picking at random? It's just if they were equally likely, right? Where is it? It says whether the sample data provide convincing evidence that the left front tires picked more often than we would expect if the four tires were picked equally often, so purely at random. So let's go back and we're gonna get to write our hypotheses, which I've already been having you practice writing the null and alternate hypotheses and talk about what that is, but in this section we're gonna go more in depth into what each of them represent. So because I want to focus on the left front tire, I'll make the variable binary, so we already talked about that, left front or not. And the parameter of interest then is the long run probability that an ARC student picks the left front tire. So what symbol will we use to refer to this parameter? And we're going to use P because that is for the population. So P will be the population proportion of all ARC students who pick the left front tire. So based on a research conjecture, now let's write both the hypotheses, the null and alternative hypotheses. So here I kind of give a big definition, a key idea of what are these statistical hypotheses. So the hypotheses are a statement about a population parameter. So our hypotheses are always written about the population parameter, which is why it's important to identify which one is the population. So P is the population, P hat is the statistic. So null and alternative are always written about a population parameter. So P or mu, depending on whether your variable is categorical or quantitative. Carefully state a pair of hypotheses, one that represents the claim, the other is its complement. Most often. So when one of these hypotheses is false, the other must be true. Either hypothesis, the null hypothesis or the alternative hypothesis, may represent the original claim. So it's not necessarily the alternative hypothesis is always the claim, but it's very likely that the alternative is the claim. The null hypothesis, denoted H null or sometimes pronounced H naught, is a statistical hypothesis that contains a statement of equality. So your null hypothesis always has either the less than or equal to, just plain equals, or greater than or equal to. The point is it always has some sort of equals, while the alternate hypothesis does not. So it's always going to have either the greater than, the less than, or the not equals. So here are some examples of null and alternate hypotheses in symbols. So if it's about the mean, you can have the mean is less than or equal to k, and oops, that should be greater than, and that should be less than, right? The opposites. So if the null is that the mean, the population mean is less than or equal to k, then the alternative is that the mean is greater than, and so on and so forth. And these are about a proportion. So P equals to, and these I just changed the symbols, but it could be, right, I could have a P there. And then now notice here, this is why I said here most often, the alternative hypothesis is most often the complement of the null hypothesis, but it doesn't have to be. So here, P greater than K, and the P equals K is not the complement. So these are not complements of one another, right? Complement is the negation, so P equals K. The complement of that will be P not equal to K. But this is still a form of a complement, right? It's P greater than K is still not equal to. So it's just, so I don't want you to think it's a direct opposite. So it just doesn't have to be, it doesn't have to be the direct opposite. So complement could mean different things. So P equals to K is complement is just that P does not equal K, but P could be greater than K, P could be less than K as long as it's not equal to K. Hopefully that makes sense. So let's try an example. A researcher claims that 51% of US adults believe incorrectly that antibiotics are effective against viruses. In a random sample of 2,202 adults, 1161 say antibiotics are effective against viruses. Write the null and alternative hypotheses. So since we're talking about percentages of people, so we have a proportion. So I'm going to just copy one of these, just to have like a little template for, in my symbols, for the null and alternative. So this is not necessarily what they are, but we're talking about P. So I'm just copying and pasting so that I don't have to recreate them. Okay, so the null and alternative hypotheses are always about the parameter, so P, not P hat. And so let's see here, which one is the parameter and which one is our claim? So a researcher claims that 51% of US adults believe incorrectly that antibiotics are effective against viruses. And this, I guess it says incorrectly because antibiotics fight bacteria, not necessarily all viruses. So anyway, 51% of adults. So is that a parameter or is that a statistic? And then notice here in a random sample of 2202 adults, 1161 say antibiotics are effective against viruses. So the question is, which one is the parameter and which one is the statistic? Statistics refer to a sample and parameters refer to the population. So here, because this is in a random sample, that means that if I do 1161 out of 2202, that's going to be my statistic, so my p hat. But the null and alternative hypotheses are about the parameters. So the 51% is my parameter. So that's what I want to use. So then the researcher claims that 51% of US adults believe. So it doesn't say more than 51 or less than 51. So that is an equality statement. So my claim, so here is going to be the null hypothesis. So P equals 2.51. And this happens to be the claim. The researcher claims that 51% of US adults believe that antibiotics are effective against viruses. So because it doesn't say more or less, then that is inequality. So P equals 51. And the alternative will be then P is not equal to 51%. And this will be the direct complement. And the reason I will know whether to say greater than or less than, that is in the wording it will say more than or fewer than, things like that. So there'll be something in the wording that will prompt you to use a less than or a greater than for either for the alternative. So whether that's the claim or not, you'll be able to tell based on the wording. So that's an example. So the main thing when writing your hypothesis is being able to decipher which one is the parameter and which one is the statistic, and be sure that your null and alternative are written about the parameter. So for the tire, so going back to our tire study, let's write our null and alternative hypotheses. So let's go back and see the claim. So we want to see conduct a test of whether the sample data provide convincing evidence that the left front tire is picked more often than we would expect if the 4 tires were picked equally often. So purely at random. So this is one of those where, okay, so I see more often, so I'm going to have a greater than we would expect if the 4 tires were picked equally likely. Now, if the tires were picked equally likely, what do you expect the probability of picking the left front tire would be? It will be 1 out of 4, right? So then our null hypothesis, and so I'm just going to copy this one again. So our null hypothesis is going to be that P is 0.25 if they're picked equally likely. And then if they are not picked equally likely, my claim is that students pick the left front tire more often. So what does more often mean? It will be greater than 0.25. And so this is one of those where we don't have necessarily a direct complement, right? So it's not a negation completely. So the proportion is 0.25, and here the proportion is greater than 0.25. So again, the null hypothesis always has an equality of some sort, equals, greater than equal to, less than equal to, or in the alternate hypothesis is the non-equals. So those are our hypotheses. Is the sample proportion who selected the left front tire greater than 1/4 for our sample? What was our p hat? Our p hat was 0.30. So is that greater than 0.25? Yes, barely, but it is greater. So that means we can keep going. If you do not have, if not, there's no need to conduct a test of significance, right? Because we will have no evidence that this tire is selected more than 1/4 of the time in the long run. So the researchers will have to do something different or create a different conjecture. So that's what this is saying. So let's do a hypothesis test now. What is a hypothesis test or a test of significance? This is a procedure for testing a claim about a property of a population. So no matter which hypothesis represents the claim, so back in this example, the null hypothesis was the claim. And in our tire study, notice that the alternative hypothesis is actually the claim, the conjecture. So that's why it doesn't matter which one is the claim. Always begin the hypothesis test assuming that the null hypothesis is true. So we're always going to assume that the null hypothesis is true. And then we perform the test of significance. And so we're going to have one of two decisions will be made. We'll either reject the null hypothesis or we'll fail to reject the null hypothesis. And this one always kind of causes confusion because this doesn't mean we accept the null hypothesis. So we just fail to reject it, meaning there's probably something else going on. So because your decision is based on a sample, there is the possibility of making the wrong decision. So what does it mean to make the wrong decision? The null hypothesis is true, but we reject it. So that's a type 1 error. And then the other type of error is the null hypothesis is false, but we fail to reject it. And so that is a type 2 error. We will focus on the type 1 error. So we'll now test our claim for the tire problem using a 0.05 as the level of significance. And the decision criteria for the p-value method in deciding whether to reject or fail to reject is going to be that if our p-value is less than alpha, then we'll reject the null hypothesis. And if the p-value is greater than alpha, then we'll fail to reject the null hypothesis. And let's see, what is a level of significance? So that here's a definition of that. So a level of significance is your maximum allowable probability of making a type 1 error. So remember, a type 1 error is the null hypothesis is true and we reject it. So that is a type 1 error. So our level of significance is the maximum allowed probability of making that type of error. So this is our alpha. And so we set the level of significance at a small value. we are saying that we want the probability of rejecting a true null hypothesis to be very small. So you always see this alphas, the level of significance, to be small because we don't want to have a high chance of making a type 1 error. We want the probability of making a type 1 error to be very small, right? We don't want to make a type 1 error often. So that's where a level of significance comes. The level of significance, it gives us the probability of making a type 1 error. So we want those alphas to be small. 0.05 is the one used most often, and that's what we're going to use for our sample. Sorry, I keep scrolling. Hopefully I'm not giving you a headache. To test our hypothesis, first we need to identify our test statistic for our study based on the variable. And this is where things get a little crazy as we go through all the different sections. Right now, we're focusing on the proportion, the population proportion. So we're going to use the binomial approximation to normal. And these requirements that you see here is really the central limit theorem requirements, right? NP, the approximation to the normal with the central limit theorem, says that your size of the sample times the probability of success has to be bigger than 5. And the size of the sample times the probability of failure has to also be bigger than 5. So this essentially just says the number of successes has to be more than 5 and the number of failures has to be greater than 5. And then we use our z-scores to find our test statistic for a proportion. And then when your variable is the mean, then if we don't know sigma, the central limit theorem, right, you have to have a sample greater than 30. And when we don't know sigma, we use the t distribution. And so this is the test statistic for that, or t-score. And then when we do know sigma, the population standard deviation, then we go back to using z-scores. And we were doing this when we did confidence intervals. And this is our, we go back to z-scores. And then if our variable is the standard deviation or the variance, we use the chi-square distribution. And then this is our test statistic. So next we look up the p-value using our test statistic, and then we decide whether we reject or fail to reject the study. So let me actually, just for the notes to make a little more sense, let me move this to after the p-value. I think that makes a little more sense than the way that I had it, in order to decide how do you reject, what do you do with your null hypotheses. So a p-value in a hypothesis test is the probability of getting a value of the test statistic that is at least as extreme as the one obtained in our sample data. So how likely are we to get our sample, right, or in this case our proportion. What was our proportion? We had, it was 0.3, I think. Yeah, 0.3. So the p-value is how likely are we to get this? And then we'll compare that to our level of significance. So let's recap our study. Recall our hypotheses from part G, and then recall our sample statistic from part E. All right, so here are our hypotheses, or null hypotheses, is that the probability of choosing the left front tire, if it's just, we're just picking at random, is 0.25, 1 out of 4. And the alternate hypothesis is that the probability of choosing the left front tire is more than 0.25, and this is actually our claim. So when we run a test of significance, we're always assuming that the null hypothesis is true. So our sample statistic is b hat equals to 0.30. So now we're going to conduct a strength of evidence. So based, using 0.05 as the level of significance, would you reject or fail to reject the null hypothesis? All right, so how do we decide that? Let's go through what we have to do. We have to find our test statistic. Well, first probably check that the requirements are met, then find the test statistic, and then find the p-value, and then make the decision whether we rejected or not. So let me type those up real quick. So essentially, to perform a test of significance, these are what you have to do. Check the central limit requirements for your particular example. Find a test statistic corresponding to your variable, so p, mu, sigma, or sigma square, right? The population proportion, population mean, population standard deviation, or population variance. Look up the p-value in the corresponding table, whether it's z-scores, t-distribution, or chi-square, depending on your variable, and then compare your p-value to the significance level alpha. And so here, because we're dealing with the population proportion and sample proportion, we're going to use a z-score sampling distribution. The requirements are that the number of successes has to be greater than 5 and the number of failures has to be greater than 5. So here, our proportion is 0.3, but when the number of successes will be 11, right? 11 people chose the left front tire. So is that bigger than 5? Yes. So, and then the number of failures will be the people who didn't choose the left front tire. So if we scroll up to that page where we had the data, right? So 11 people chose the left front tire, so that's more than 5. How many people did not choose the left front tire? You have a lot, right? 12 plus 8, that's 20. So 26 people didn't choose the left front tire, so that's more than 5. So our study fits the criteria for the central limit theorem. So NP is greater than 5 and NQ is greater than 5. Next thing is find the test statistic corresponding to your variable. So going back to this table, this is going to be pretty important. So maybe bookmark it, save it somewhere, take a screenshot, put it somewhere where you're going to be able to see it, print it. So our test statistic is z equals to p hat minus p. So their sample statistic minus the population parameter divided by, and these are not hats, these are from the population. So let's go do those. So bringing you over to my notebook here. So let's go. So we already said it meets the criteria for the central limit theorem. And now let's find the test statistic. Because we're using a proportion, then I know I'm going to use z. So z equals p hat minus p over the square root of, what is it, pq over n. So p times q over n. So for our particular sample, we know that p hat is 0.30. P is, how do I get my p? This is from our null and alternative hypotheses, which is why I had us recall them over here. So we have our p hat, our sample statistic is 0.3, and our hypothesis is that p is 0.25. So that's what we're going to use as p. So p is 0.25 and q is going to be then 1 minus 0.25, so 0.75. And so when we do our test statistic, then this is going to be z is equal to 0.3 minus 0.25, right? P hat minus p divided by the square root of pq over n. So I'm going to have the square root of 0.25 times 0.75 over n. The size of our sample was 37. Should have included that in there. So when you're doing a test of significance, find your sample statistic, your population parameter, and then your q. If it's a proportion, then you need to find p and q, the probability of success, the probability of failure, and then the size of your sample. And so let's put that in our calculator, which after putting it all through, I get 0.7024, so 0.7024. So this is my z-score. And so now, right, so look at my steps again. So find the test statistic, look up the p-value in the corresponding table. So because I'm using z, we're going to look up in the z-score table and look at our p-value is the probability of obtaining our sample statistic, 0.30, the likelihood of obtaining this value. So our p-value, let's go to the z-score table. So in this case, you will go to the z-score and we're looking for 0.70. So just 0.70. So let's see, 0.70 is right here. So we can say 0.7580 is our p-value. Well, or is it? Notice that our claim is that p is greater, or proportion is greater than 0.25. So I want then, when I'm looking at my p-value, is the probability then that z is going to be greater than, right? I want to see if I'm going to be greater than more often. So let's go back to my notes here. So our p-value is, and let me write out what I'm looking for, is the probability that z is greater than 0.70, right? What is the probability that our population proportion is more than 0.25? So we want to see how likely are we to get this. But remember, our z-score, looking at the table and the graph, this gives us the area to the left, but what I want is the area to the right. So that means this is going to be 1 minus the probability that z is less than 0.70, rounding to 2 decimal places. So let's go back to our table and let's see, 0.70. And the reason I round to 2 decimal places is because the z-scores are only round to 2 decimal places. So 0.70 is 0.7580. So this is going to be 1 minus 0.7580. And so when we do this on our calculator, we get 0.242. So this is our p-value. So now we want to compare our p-value, looking at the steps, compare your p-value to the significance level alpha. And then we're going to make our decision whether we reject or fail to reject H naught. So we're going to compare our p-value versus alpha. So our p-value is 0.242 and our alpha is 0.05. This is the level of significance given. So what can we say? What's the relationship? Greater than or less than? Our p-value is greater than alpha. So what do I do? So going back to the notes, the decision criteria for the p-value is if the p-value is less than or equal to alpha, then we reject the null hypothesis. If the p-value is greater than alpha, we fail to reject the null hypothesis. So this is the case that we have. So that means that we fail to reject the null hypothesis. So we fail to reject the null. And remember, the null was that the probability, the proportion of people who choose the left front tire is 0.25. So we fail to reject that. So what does it mean we fail to reject? So that means that this could be true. It could be happening that people are just choosing at random. So we can't ignore that this could happen, right? The fail to reject the null means that the null could happen. Rejecting the null hypothesis means it definitely can't happen. And so here, fail to reject, it's like, okay, so the null hypothesis could be happening, so people could be choosing the left front tire just at random. What does that say about my claim? The alternate hypothesis was the claim that people choose it more often. And so now we can say, well, that's probably not happening because we can't reject the null. The null is saying people are choosing the left front tire at random and we can't reject it. So likely my claim is wrong. People are not choosing the left front tire more often. A good example to another good to maybe try on your own is the baby study that we did back in chapter 5, I believe, and where that it was the researchers, we watched the video and everything, and it was whether babies can recognize friendly behavior versus unfriendly behavior and choose the friend toy because they recognize the behavior rather than choosing at random. So that will be a good one to go through and look at the what is the null hypothesis, what is the alternative hypothesis, and in that one you actually reject the null. And so try it on your own. I'll record a video doing it as well, but I want you to try it on your own. So for the baby study, which was in chapter 5, you can go to that module and remind yourself. It's easy to find it by looking at where the video is, in which module is the video. It's called friend or foe video. And then look at the null, look at the alternative, and then look at our sample statistic was like 14 babies out of 16 chose the friendly toy. And the claim is that babies can identify friendly behavior, and that's why they're choosing the friendly toy. So can we do a test of significance at the 0.05 level and make a decision? So try that, and then I'll record a video doing just the baby study as a test of significance, and we'll see what we get.